Okay, good morning, everyone. Let's see. All right, today we will wrap up series parallel analysis technique, and then we'll go into voltage and current division, and then, if time permits, node voltage analysis. Now, before I begin, how many of you know how to use MATLAB? Several of you, that's good. MATLAB is a very powerful computational tool for engineering, especially. Mechanical engineering, electrical engineering uses MATLAB very heavily. If you go to any job website and search for job postings in your field, I guarantee you more than 50 to 60% of those postings will have MATLAB listed as a skill. So it's important that while you're still in college, you learn how to use the software tool. Okay. When I was a student, we didn't have that. And so I'm kind of learning after the fact. Okay. So I'm by no means an expert in MATLAB. But what I want students to do is you download MATLAB from Cal Poly's website. Well, actually, not Cal Poly's website. Cal Poly has an institutional license, meaning all students, staff, and faculty can use their Cal Poly IDs and activate MATLAB on their own devices. So you download that on your laptops and your desktop computers, download it on your tablets or your smartphone. It works on a phone too. And we will use it to solve linear equations. If you've never used MATLAB, start at the beginning, meaning use it as a basic calculator. Literally, the first thing I typed in when I first started learning was 2 plus 2. That is literally the first thing I typed in, 2 plus 2. And that's how I started learning it. So again, this is not a MATLAB class, but I do want students to have the opportunity to learn it. So you can solve linear equations with a variety of methods, right? You can just solve them manually. You can use your calculator. If you have a programmable one, you can program equations in it. You can also use MATLAB to solve those kind of equations. Again, it's a very powerful computational tool. So as an engineer, it's a very good skill to have on your resume. Yes. There are several software tools that can do that. SPICE is I wouldn't say that. SPICE is a program that was developed in the 60s at UC Berkeley. It's called, I can never remember the full form of that acronym, but it's called SPICE, S-P-I-C-E. It's simulation for integrated circuits. So ICE stands for integrated circuit emphasis, and S is for simulation. And there are multiple versions of SPICE. So now there is a software that's available for free called LT SPICE by Linear Technologies. You can create a circuit diagram in there, and you can run a simulation, and it'll give you the voltages and the currents for every single component in there. And so that's something I plan to show in my labs. Okay, so let's see. Let's continue with our topic of discussion, which is series parallel equivalent analysis. So there are 3 examples on the next page, and I am going to do 2 of them in class. Okay, I will leave A for practice. I will set up problem A, but I will leave students to practice. Okay, so if you look at A, by the way, do students prefer red ink or black ink when I write it on the board? Which is better? Let me write out both, and then let's see. There's a variety of colors, but either red's better. You view them at your own end in the class notebook on your end, and then again, you can give me feedback if you wish to. So for A, we are asked to solve for the currents, right? But it's not just currents. I mean, you could solve for any quantity in the circuit. You can solve for voltage, you can solve for current, and then once you have both, you can solve for power for every component. So in this case, the currents are already given to us along with your current direction. Okay, I1, I2, I3, I4. If we want to solve a circuit using the series parallel analysis technique, we have to remove the source and find Req at the terminals where the source was connected. So the circuit diagram would look something like this. and we would find Req between the open terminals. So what do we see? We start at the farthest end and we move towards the measurement terminals, reducing the circuit step by step. Evidently, intuitively, we can just look at these circuits and we can say R4, R3, and R2 are in parallel. Would you agree? Right? Because they have two terminals and the respective terminals are connected together. So all three of those are in parallel. And then once you reduce those, and let's call it R5. R5 is equal to the parallel combination of R4, R3, and R2. Right? And then R1 and R5 are connected at one single node. There are no more than two connections at that node, so they are in series. And because they're in series, we simply add them up. So our total Req measured between those terminals is R1 plus R5. Again, in this case, it's a simple calculation. And then you plug it back into the circuit. And you can calculate the total current I that is being supplied by the power supply, voltage Vs. Right? Now, if we go back to the original diagram, current for a supply always goes from low to high, from minus to plus. So that current goes through R1. Whatever current the supply is sending out is flowing through R1, reaches the top node, and then it splits in three. So now the step after this would be to find the total current IS. I will label it as IS. IS would also be the current that flows through R5. IS, R1, and R5. You guys with me so far? And then if the current is going in this direction, which side is plus and which is minus for R1, left or right? Left is positive. Point of entry for a resistor, for a passive component, is always positive. So the voltage drop across R1 would have a plus on the left, minus on the right. How about R5? How many of you agree? Positive up top, negative at the bottom. Then you can calculate VR5. That simply be IS times R5. Once you have VR5, you expand the circuit back to its original state, and VR5 would be the same voltage across that entire parallel combination. And then you can apply Ohm's law again and find the current I2, I3, and I4. So take 10 seconds. Let me know if you have any questions. As long as you understand the method, the step-by-step layout of problem solving, that's the most important thing. Everything else after that is just basic calculation. Yes. Yeah. Yes. Yeah. So the question being asked is, what if you have a battery symbol? In this case, it actually doesn't make any difference. A battery is noted with this kind of symbol. It's two parallel lines, a capacitor, if you remember from your physics classes, is two parallel lines of equal length. A battery is indicated by two parallel lines of unequal length. One is longer, one is shorter. The longer one indicates the positive terminal, the smaller one indicates the negative terminal. A battery falls under the umbrella of a voltage source. Okay, so a battery can be described as a DC voltage source. That's the answer to the question. In general, we simply use this symbol right here, the circle with a plus and a minus, to just indicate that it's a source, voltage source specifically. And then, of course, a battery falls under the DC voltage source. Any other questions? Okay, let's take a look at B. The first thing is that the source is a current source, right? It's a current source. And again, as a reminder, in real life, a current source and voltage source are exactly the same physical box, right? If it runs in constant voltage mode, it is referred to as a voltage source. If it runs in a constant current mode, we refer to it as a current source. You cannot have one without the other. So we have current of 2 amps. This problem I like. I specifically chose this problem because you do not need any engineering analysis to solve this problem. Okay, you could show this to any layperson and you can just use logic and intuition to solve it. But let's use engineering analysis first. Relationship between R1 and R2. How about the other two? Once you reduce those, right? You already know your stuff. So what do we see? And this time I'm skipping over the step where I remove the source. But anytime you analyze, if you're not yet certain, then you take it step by step, okay? So you remove the source and then you find REQ from the perspective of the source. So this is 20, this is 20. 2 amps. 20 and 20 in parallel gives us, remember the shortcut? If you have multiple resistors in parallel with the same value, the answer is R over N. R is 20, N is 2, so 20 divided by 2 gives you 10 ohms. You could also do product of the two divided by the sum of the two, which is 20 times 2400 divided by 20 plus 20, which is 40, again, 10 ohms. So 2 amps and 10 ohms voltage across the current source is equal to the voltage across the resistance, which would be 20 volts. So if this is IS, I'm going to call this VS, and VS is 2 times 10, gives me 20 volts. Straightforward, easy enough, right? And 20 volts divided by, well, 20 volts appears across the current source, 20 volts appears across the first branch, 20 volts also appears across the second branch. It's parallel circuit, so 20, 20, 20. Voltage remains the same. So apply Ohm's law, and you can find I1 as equal to 20 divided by 20, 1 amp, and the same thing for I2. Sorry, I forgot to silence this. Make sense? Any questions? Any questions about the analysis? Yes. I1. So it's 20 volts across the current source, 20 volts across the first branch, 20 volts across the second branch. So we simply apply Ohm's law, V equals IR, I is equal to V over R. So let me write it down there. I went a little fast, but I would be Vs over R. Now, let's look at it logically. You have a current that's coming up and going through the circuit, reaches the junction, it splits in two, right? The traffic down both streets is exactly the same. So it's going to take the same amount of time to cross and go down that pathway. 15 plus 5 gives us 20 ohms, 10 plus 10 gives us 20. It's an equal split. So the current is splitting in two, but the split is exactly equal. So logically, you could say 2 amps splitting 2, 1 plus 1. And I think several of you recognize that immediately as soon as you saw the problem. So that's good. All right. C. You tell me. At the farthest end, what do we have? R4. Next resistor up is R3. Series. So how much is it? 40. Right? So R4 plus R3, 40 ohms. Then up next is R2. Is it parallel? 40 in parallel with 40. How much do you get? 20. So R2 is in parallel with R4 plus R3, which would give me 40 divided by 2, 20 ohms, which is then in parallel or series with R1? In series with R1. So that is REQ would be R1 plus R2, which is in parallel with R4 plus R3. That's the entire equation. I'm deliberately doing this in the form of an equation because it is another method by which you can show your work. Okay, you can show your work by drawing out the circuit diagram for every step, or you write out the equation in this manner, or you can do both. It's 10 plus 20 equal to 30 ohms. And then look, Vs is also 30. So if Vs is 30, total current Is from the source is equal to Vs over Req. So equal to 30 over 30 gives me 1 amp. And then you expand the circuit back up again. Is would be equal to I1. So Is, sorry, it's appropriate to say I1 is equal to Is, which is equal to 1 amp. And then that 1 amp is split equally between two parallel branches, 40 and 40 ohms. So it gives us 0.5 and 0.5. So I'll give you the answers, right, logically, but you should practice writing out the equations. So I1 splits into I2 and I3, and it's an equal split. So I2 is 0.5 amps. I3 in the second branch is also 0.5 amps. Practice. Write out the equation by using Ohm's law. Find the voltage across that branch. Find the voltage across R2. Find the voltage across R3 and R4. You don't have to find the voltage across R3 and R4. You can find it across the combination, but again, it's a good practice. Okay, good practice. All right, any questions? So the homework on this topic is due tonight. If you have any questions, reach out to me. I have office hours in the afternoon. I'm also teaching the lab in 126. So while I'm teaching the lab, if you have any questions, you can come on by. Just send me an email. And if you have any questions, I'll be happy to answer them. Okay. All right, let's take a 10-second pause before we move on. Think on this. Let me know if you have any questions. Yes. So the question being asked is there a specific way to determine when we are splitting? Oh, because, yeah. So let's see. Let's slow down a little bit. So from this step right here, I'll draw up the circuit. So we have R1, and then we have, let's call this R5, which is the combination of R2 and R3, right? So this was 40 ohms, and this is already R2, right? 40 ohms. So this is R2, which is 40 ohms. And so IS is coming from the source, goes through R1, and then it splits in two. So 1 amp coming in the junction and splitting into two, and it's an equal split, 40 and 40. And that's how we can know it's 0.5 and 0.5. But again, as I said, once we reduce this, R2 and R5 in parallel gives us 20 ohms. So we can find the total current flowing through the circuit, which is 1 amp going through 20 ohms. So it's 20 volts across both resistors in the parallel. And then you apply Ohm's law, 20 divided by 40, 0.5. Make sense? Right. Now, again, you're going a little bit fast, again, because this is prereq material. Typically, this would be covered on the Friday of the first week. All right, any other questions before I move on? Okay. So 2 more topics before we delve into a circuit analysis technique. There are 2 shortcuts we can use, both of them derived from Ohm's law. The shortcuts are to determine the voltages in a series connection and currents in a parallel connection. And both of them are basically noted as voltage division and current division. So it's a division. Okay, voltage division, current division, they are both shortcuts. If you have looked at the final exam page, you will see that this will be asked in the final exam. Okay, this will be asked in the final exam. It's listed on the final exam page. So if you're not yet taking a look, go ahead and take a look. It's not that difficult, right? It's not that difficult. It's basically derived from Ohm's law. Let's start here. V total is the source that is being applied. Current would go in this direction. It's a series circuit. What happens to current in a series circuit? It's the same. Nothing happens to it, right? The current in a series circuit is a result of all the resistors working together. Whatever value you obtain is the same for all of them. So current never gets divided. Current remains the same. However, depending on the value of the resistors, the voltage would be divided. So total voltage is being applied across. Now, I'm showing the derivation. That's not something that I want students to understand the derivation, but I'm not going to ask the derivation in the exam. In every topic in this class, in this course, what I will assess is your understanding of the material and how you can apply that knowledge. That's what I'm going to ask you. I'm not going to ask you to sit there and derive this. So V is equal to V1 plus V2 plus V3, the series connection. Total V would be given by I1 plus R2 plus I times R3. It simply gives me I R1 plus R2 plus R3. So total voltage V or V total, let me just write down VT, is simply given by I times REQ. Right? I times REQ. So then if I wanted to find the single voltage V1, V1 is a fraction of the supply voltage V total VT. Okay, the total voltage that is applied to that entire connection. Okay, it's a fraction of that total voltage that is being applied. And that fraction is given by R1 or REQ. Okay, R1 over REQ. It's simply a shortcut. I think I skipped a step in there. Hold on. Sometimes I have to actively think that this is not an E major class. Does that make sense now? Okay. When current flows through, when you apply total voltage to a series connection of resistors, a current flows through that series connection. That current is the same for all. We find the current as given by the total voltage VT divided by REQ. That current is flowing through R1 to R2 and to R3. So when you find V1, V1 is that current I times R1. We rearrange the terms and we get VT times R1 over REQ. So again, it's derived from Ohm's law. It's derived from Ohm's law, but it's a shortcut. It allows you to skip a couple of steps. You don't have to find the current because you can find the voltage directly from REQ. VT over REQ gives you the current. So it saves you one step. And V3 similarly is VT times R3 over REQ. Okay. The voltage that appears across each resistor is a fraction of the total supply voltage, and the fraction is given by the ratio of the resistor to REQ. So R1 over REQ, R2 over REQ, R3 over REQ. REQ in this case is the sum of the resistors in the series connection. Okay, nothing else. But let's look at an example. 4 resistors in series, 1, 1, 2, and 6. REQ as seen by the voltage source. Simply 1 plus 1 plus 2 plus 6. 10, not volts, 10 ohms. 10 ohms. Now, yes? Sorry, what? Oh, yeah. Thanks for pointing that out. Yes. That's something I point out to students all the time. Don't forget the unit prefix. 10 kilo ohms. 10 kilo ohms. So 10 kilo ohms and 15 volt source applied to it, you can find the current, but a voltage division is a shortcut. So you can find VR1 as a fraction of the supply voltage VT times R1 over REQ, which would be 15 times 1000 divided by 10,000. 1.5 volts. Let's take 10 seconds, think over that, and let me know if you have any questions. Yes. Yes. The question being asked is this voltage division applicable only to series circuits? The answer is yes. Because in a parallel connection, voltage remains the same. So voltage doesn't get divided in a parallel connection. So yeah. In a series circuit, current remains the same, voltage gets divided. In a parallel connection, voltage remains the same and the current gets divided. And so it applicable only to series circuit and current division only applicable to parallel circuits. Okay, let me wipe out VR1. Let me just call it V1 because the diagram already has given me V1, V2, V3, V4. What is V4? Vt times R4 divided by Req, 15 times 6,000 divided by 10. How much? Anyone? And then same way you can find R3 or V3. Easy enough? Is voltage division and current division covered in physics 3? No, so this is something new, right? Okay. Again, as I said, it's not an analysis technique. It's a shortcut that is derived from Ohm's law. It's a shortcut. Okay, but students, it's there on the list of things that we are required to teach. And so, well, that's what you're doing. Devote a couple of slides to it. All right. Voltage division is relatively straightforward to apply. Current division, from my past experience, is where students have some trouble. So current division. There are a couple of ways to apply current division, but we'll stick to the simplest one. Okay. I total, let me just call it IT, is being applied to that circuit. Okay. I total is being applied to the circuit. When it reaches the junction, now this example uses a current source, but in a larger circuit, it doesn't have to be like a current source. Yes. This is only for resistors for now, but when we get to AC analysis, we model inductors and capacitors as impedances, and you can apply current and voltage division for AC analysis also. So in that case, it will apply for capacitor and for a inductor. Good question. The question being asked was, does it apply only to resistors or does it apply to inductors and capacitors also? And so the answer is, when we get to chapter 5 and do AC analysis, when we model capacitors and inductors as impedances, we can apply these techniques. So let's see. Voltage V in a parallel connection remains the same, right? So the total current I total being applied to these resistors is going to remain the same. So in current division, V is same, and I current is divided. And again, current division is a shortcut derived from Ohm's law. Vt in this case would be equal to IT times Req, which is IT times the parallel combination of R1 and R2. You can have infinite resistors in parallel, but you find Req for all of them. Okay, all the resistors in that network. So this example just shows you two, but you could have infinite resistors in parallel. So you find Req, and then you can find, let's see, to find current I1, voltage, again, as I said, voltage is the same for all of them. You apply Ohm's law. This is VT over R1. You plug in the value for VT, which is IT times Req. That's the expression you obtain. When current is applied to a parallel connection of resistors, a fraction of that total current appears or flows through each individual branch. And the fraction is given by the ratio of Req to the resistor R1. Take 10 seconds, think over it. Let me know if you have any questions. For voltage division, it was R1 over Req. Req was in the denominator. For current division, Req is in the numerator. The structure of the equation is the same for both. Make sense? And then I2, similarly, we found as Req over R2. Okay. Again, this is a shortcut derived from Ohm's law. So there's not a new analysis technique. It's simply a shortcut. Allows you to skip over one step. You good? Then let's look at an example. 10, 30, and 60. Take out your calculators. Tell me what Req is. Req should be 1 over 10 plus 1 over 30 plus 1 over 60. Anyone online who is doing this calculation? What answers do you receive? If you have MATLAB on your smartphone, you can type this in there. Anyone? 6.6667. Does everybody have the same answer? Okay, that is correct. So, as an example, I1 would be equal to the total current IS times Req or R1. IS is 15 amps. Req is 6.667. Also, one indicator, 6.667 is smaller than 10, which is the smallest value in that network. I hope everybody remembers that from last class. So what is this answer? I1 is equal to? Anyone? 10? 10, I heard 10 from 2 people, 3 people. 3 persons telling me 10, going, gone. There's logically you can solve this. You have 10 ohms, 30 ohms, and 60 ohms. 30 is 3 times 10. 60 is 6 times 10. Current is inversely proportional to the resistance. So whatever value you get for 10, current for R2, I2 would be 3 times, the ratio would be 1:3. Current for R3, I3 would be 1:6. Or 6:1, 3:1. Okay, I'll leave you to practice I2 and I3. Okay. Now we get into the meat of circuit analysis. Node voltages and mesh currents. Okay. This is where all the techniques that we learn in physics, that we learned in the first week of class, this is where you'll apply this. The concepts that that are required to solve for these would be KCL, KVL, node voltages, and mesh currents. You are familiar with KVL, you are familiar with KCL. I will explain what node voltages are and what mesh currents are. Okay. Now, when you look at this diagram, just a standard circuit, you have a voltage source Vs, right? You have 4 resistors, R1, R2, R3, and R4. This is supposed to be R3. Corresponding voltages, V1, V2, V3, are listed on there, along with the polarities. We'll put a pin in IA and IB for now. We'll leave it to the side. So what is a node voltage? Well, we know what a node is, right? A node is a junction of 2 or more components coming together. That's a node. The voltage measured at that node is a node voltage. But the concept is, if you are measuring voltage at one single node, what is my reference point? Because voltage is always measured as the electric potential difference between any 2 points, right? So you need a baseline, you need a point of reference. So node voltages are typically measured where the negative end of the power supply is connected. It may be marked as ground, it may not be marked as ground. Ground, by the way, is a symbol that is indicated by 3 parallel lines shaped like a triangle. Sometimes, or some authors like to use a triangle itself. Sometimes it might just be a simple dash or a simple line. All of these indicate ground. The acronym is GND. Okay. So whether ground is indicated in the circuit or not, it doesn't matter. You take the negative end of the power supply as your reference point. And that reference point is the point of reference for all voltages in that circuit. So when we say node voltage, you measure the voltage at every single node. In this case, in the circuit diagram, you have 1, 2, 3, and 4 nodes. Node A at the bottom is shown as connected to ground, and that is a reference node for the rest of the circuit. Okay, for the rest of the circuit. So we saw in chapter 1, the 2 subscript notation for voltages, right? VAB means you're measuring voltage at A with your point of reference at B. VA would be the node voltage if B was noted as the reference point for the entire circuit. So here's where we talk about the single subscript notation for the voltages. Okay, single subscript notation. So 2 subscript notation, we had VAB, meaning A is plus, B is minus, voltage measured at A with my reference at B. Or VBA would mean voltage measured at B with my reference point at A. Everybody remember that, right? 2 subscript notation. Node voltages use a single subscript notation. Okay, node voltage, I'll write this out. Node voltage uses a single subscript notation. So in this case, A is my reference node, and that reference node is used for all voltage measurements. So VB in this case means I'm measuring voltage at B with my reference at A. That A is implied. This is a very important concept for students to understand. The A is implied. And because we choose this as a reference node, For the purposes of analysis, VA would be equal to 0 volts. It doesn't matter what the actual voltage is at my reference node. I can choose any node as reference. I can choose B, I can choose C, I can choose D. You can choose any node as reference. It doesn't really matter for the purposes of analysis. But if you choose a node as reference, then you stick with that assumption until you end your analysis. You cannot change that reference halfway through your solution. Okay. So again, this is again very critical to understand. You can choose any node as your reference measurement. It doesn't matter whether it's the positive end of the power supply or the one of the ends of a current source. Once you choose that node as a reference, that node has a value of 0 volts for the entire analysis. Yes. 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 And we will see, yes. So the question being asked is, if we choose B as a reference node, isn't it likely that the other nodes are negative? And the answer is yes. If you choose one node as a reference, you could have other node voltages turn out to be like negative values, which is absolutely fine, right? A reference is just a baseline level of measurement. It doesn't matter whether if this is my baseline right here, the voltage could be up, could be below. It could be above or below my reference. If it's above the reference, I would get positive answers. If it's below the reference, I would get negative answers. It does not mean your answers are incorrect. Okay, I would look at the reference that you have chosen, and then I would look at the values, and then we would know that it is correct. And we will see this in the example problem that I have on the next slide. Okay, I will choose a reference point in such a way that the answers we obtain would be negative. Let's see, we still have 3 minutes. Okay, so as I was saying, you can choose any node you want. That node is 0 volts. You have VB, meaning it's implied that VB is VBA. VC means it's VCA. VD means it's VDA. Now, if VA is my reference, I automatically have an answer if I have a voltage source connected to one end of that reference node. Sorry, not one end of the reference node. If one end of a power supply voltage source is connected to the reference node, you automatically have the answer at the other end. Let's simplify this. We have a voltage source. Which nodes is this connected to? B and A. If you choose A as your reference node, then VB is simply equal to VS. Take 5 seconds. Make sense? If B is your reference, what is VA? Magnitude doesn't change. If the distance between 2 points is 10, that distance is not going to change. If I look up, it's plus. If I look down, it's minus. It's minus VS. So if you have a voltage source connected in a circuit, you always choose one end of that voltage source. More likely, it's easier if you choose the negative end of that voltage source as your reference point. So you automatically have the answer at the other end of that source. Now, to take a step back, what is the purpose of doing this? We go back to chapter 1, circuit analysis. Circuit analysis is the process, is a theoretical analysis to determine the unknown voltages and currents that are present in the circuit. So our job is to use this tool, this method, to determine the unknown voltages in a circuit. Okay, to determine the unknown voltages and unknown currents in a circuit, we use mathematical equations. To generate these equations, we will apply KCL and KVL in these techniques. So we have a set of linear equations, and then we can solve those equations. The variables in those equations would be the node voltages. So depending on how many nodes you have in a circuit, those are the unknown variables you have in that circuit. So to reduce the amount of unknown variables, you choose one end of the voltage source as a reference. One end would be 0, the other end would be the voltage source. You automatically eliminate two variables. You automatically have an answer for two of those variables. Okay, so we'll end class here today, and we'll pick up here again on Friday.